today's session.
Thank you, sir.
Now I request Dr. G.P. Swami to introduce our today's affairs person.
It is my privilege to introduce Sri Prasad Naika. Who is our alumni, and incidentally, I was his teacher for 2 semesters in Tech in Real Estate Design and Design System. Prasad Narayan is a field engineering professional. Will you please maintain silence on your professors? Please listen to the speaker. Since yesterday I keep telling, but you are continuing the same thing. Huh? Being teachers, if we do like this, what can we expect from our students? Prasad Narayan is a skilled engineering professional with 17 years of experience in designing, testing and developing tools for integrated circuit design and CAD VDO. He has extensive expertise in memory design for testability, shortly DSP, including memory, BIST, built-in test, generation, insertion, and verification flows. Prasad Narayan's experience spans multiple technology nodes, including 65 nanometer, 40 nanometer, 28 nanometer, and 16 FF basic designs. He has a strong command of object-oriented design techniques, TCL programming, and familiarity with shell and periphery. With hands-on experience in synopsis, SMS-based memory test flows, and SMS 4X and SMS 5X platforms, he has worked extensively with various memory types such as SRAM, RAM, CAM, block repair, and MRI. His technical expertise includes MD-ISP insertion and verification for different memory components, RTL and netlist-based memory, DSP insertion, and proficiency in tools like synopsis, SMS 4X and SMS 5X, and logic-driven memory test flow. Throughout his career, Prashant has held key roles at Barcelona, Vapor Space, an Asian design company, Broadcom INC, and national contributing significantly to advanced DFT techniques, basic design and testing methodologies. He completed his education at Academy Energy Central School from 1998 to 2000 and continues to drive innovation in semiconductor design and verification process. I welcome Prasad. Over to Prasad.
Thank you, sir. Good afternoon, everyone. Let me first tell you the technical aspects that I am involved in, and then depending on your interest and depending on where you want to dive deep, I'll take up that topic. So basically, I'm a DFT engineer. DFT stands for Design for Test. Nowadays, they have retermed it as DFX, where X is DFT, Design for Test, DFD, Design for Debug, and DFM, Design for Manufacturing. So my involvement in the design starts with RTL and ends all the way till NPI. NPI stands for New Product Introduction. So if I'm coming up with a new chip, so it starts with the requirement spec, RTL, and finally ends with the product being introduced into the market. So we have certain terms which is very critical for us. So time to market. If we don't release a particular product into the market at the right time, then we may lose the market, or else there's no point in releasing the product maybe a few years later, because it would have lost its significance. So all this mattered to us. So as I told you, I am involved all the way from design till the NPI. So it goes through design phase, fabrication phase, and testing phase. So my interaction with the fabrication happens during the test time when we do the manufacturing test. So that's where I interact with the fab. So I'll start with some basic slides, and let me know your interest, then I can switch the topics. Okay. So before I go into testing, I want to go back a few slides and just list out the different stages that a particular chip goes through during its phase. So basically, as I told you, it starts with the spec. The spec can come from customer or client, the way we address them. So they come up with the basic spec, or what they do is certain companies, they implement the spec in RTL and they come up with the RTL. Now from RTL, we do synthesis, get the netlist, and then it goes into the physical design flow. And when this is happening, DFT comes into picture. Why there is so much stress on testing is, you all, since you are in academics, at the end of your course, you have an examination or a test for the students, and you set a minimum criteria that above this, pass, and there are other metrics depending on which you decide whether the student has passed in distinction, right? So similarly, when we have a product manufactured, and you know that the fabrication process is very chemical and process oriented process, right? Chemical and you know, right, silicon, we do all this doping, and then we do etching and all. So during this process, there can be lot of manufacturing defects that can get introduced into the chip. So when I am shipping the parts to my customer, I want to ship only good parts. I don't want to ship any bad parts to the customer, because he is not going to do any testing immediately. He is going to put that component onto the board, and then he's going to do a board bring up. And at that time, if he figures out that it has been a faulty chip which has been put on the board, he will have to completely discard the board, and that is going to cost him. So there is a terminology called DPPM, defective parts per million. If I am shipping 1 million parts, of course I cannot ship no, all 1 million parts, or I cannot claim that it's going to be good. They have to give me a margin, and that they set very little. They say 500 DPPM. So it means that they can accept maximum 500 defective parts per million parts that I'm shipping. Beyond that, any loss that they incur, I will have to bear as a chip provider. So when they set such a stringent requirement, I have to make sure that the quality of test that I am using is good and is able to catch most of the defective parts, and I'm able to meet this particular deadline. So when I have such a requirement, how do I test the chip and make sure that it is fabricated, manufactured correctly? So you might have studied about stuck-at, transition delay, bridge fault, right? There are different fault fault models available. So basically we test for those faults. This is just an introduction to why I'm stressing so much on the test, because we have to meet the quality needs. If we don't meet, as I told you, it's going to be a business loss. Now, to make this process, I would say, cost effective, because there is something called as an AT, automatic testing equipment, which is involved, which we uh, rent it out on an hourly basis, like how we rent out this JCBs or earth movers, right, per hour. So this equipment is rented hourly basis, and it's quite costly. So if you have rented it for an hour, you have to make sure that you utilize that time to test out your chips, because if you want to rent for another 1 hour extra, again you'll have to shell out more money. So if a particular chip is going to cost you $100, $30 to $40 would be coming out of all this test and packaging, and again testing post packaging. So it is like 30 to 40% of the cost, and they always want to minimize this cost. They want to reduce this 30-40%, because if you reduce the cost here, it will directly impact your profit margin. So there is a lot of stress on getting the testing done quickly, as I told you, because of cost. How do I make this happen? I should start with the way I start my design. I mean, the way I design, I should make sure that my design is easy to test. That is where DFT comes into picture, design for test. So what we do is, when the design is happening, we insert additional circuitries into the design, which is going to help us in testing. When I say testing, the manufacturing test. So that's where the concept of scan chains, BIST, that is built-in self-test, logic test, all this comes into picture during your design phase. So it helps us do this VLSI test quickly and also more efficient. So I've just listed a few steps in when it comes to DFT. So what we do is, earlier we used to do DFT at the netlist level, but now technology has advanced. We have the EDA tools also, which is going to help us. So we start DFT right at the RTL level. Most of the MBIST insertion happens at RTL level. Now, what is MBIST? MBIST stands for Memory Built-in Self-Test. See, today, most of the chips, some of the chips have close to 70% memory. If you consider the overall content of the chip, close to 70% would be memory. Now, how do you test these memories? Testing memories is a challenge. For that, we have a technique called as memory BIST. So we insert a BIST engine into the design, which is going to help us test this embedded memories. When I say embedded memories, because these memories are deep inside your design. If something is there at the boundary, which is accessible to you directly with the pin, your testing becomes easy. But if your logic is sitting deep down in the design, how do you navigate in the design to reach that particular internal point and test it? So that's where MBIST is going to help us. And then it goes to synthesis. We get a netlist. Next comes scan insertion. So scan insertion is like, there will be the sequential elements, flip-flops. So we hook up all the flip-flops into a chain, like how we have a shift register. So that is basically scan insertion. So we form something called as a scan chain. Now the scan chain is the one which is going to help us do the scan test. It is going to help us test all the internal points in the design. Now how does a scan chain works? Scan chain works exactly the way your shift register works. It's nothing but a huge shift register. One important thing that comes here is, you might have heard about compression. I don't know how much you have heard about compression, but basically my test time, when I say test time, the time required to test a particular logic depends on the length of my scan chain. So longer scan chain I have, it's like my test time will be more. So one of the requirement that is a must and should if you want to bring down the test time is to go for compression. And how is the test time calculated here? If you have a scan chain of length 100, so you need 100 clock cycles to shift in the data, and then 100 clock cycles to shift out the data, and then you need 1 cycle for capture. So you need totally 201 cycles. If my test frequency is say 10 megahertz, so then I take the period. The period is basically 10 megahertz is how many ns is it? 100 ns. So 100 ns into those many cycles. That gives me the overall test time for that particular chip. So this is how we calculate the test time. Okay. Once you have the scan insertion done, you have to go through a process known as ATPG, Automatic Test Pattern Generation. So there is a tool named Tessent over there. So this Tessent tool will help us do the ATPG, Automatic Test Pattern Generation. And we also do a simulation to make sure that, simulation is something like a design verification. Whatever you have done, how do you verify? You simulate it. Okay, so we do a round of simulation. We do coverage analysis. Coverage analysis is like, am I covering the complete logic in the design? Am I covering all the nodes in the design? Okay, so typically we have a requirement of like the coverage has to be 99%. And then I think you might have been having a session on physical design. So PD team will give us certain constraints called as SDM, and there the delays would be annotated. So we do a round of simulation to make sure that all the setup and hold violations are fixed. Okay, our simulations have to pass. That is done as a part of this PNR sign-off constraints and DFT logic verification. And as a sign-off, if I want to give a thumbs up from DFT side saying that the design is fit for tape out, all my timing simulations have to pass. Once we tape out is nothing but we send the data to the fabrication company. It could be TSMC or it could be Samsung, right? Or it could be the Intel fab. So we ship the data to them, and they will take close to 2 to 3 months for us to get the product out. Now, how does the product come out? Normally, what we get first is the wafer. So what is a wafer? Wafer is, you can imagine like, or you might have already studied, it's, you have the silicon extracted and you make slices out of that silicon. So one slice is nothing but your one wafer. And that one wafer is divided into multiple dies. Now, how many dies you can have on a wafer, that depends on your design size. So this is where the real estate in semiconductor or silicon comes into picture. So there is always a push on the PD front to reduce the die size or the design size. They'll say, can you make it as smaller as possible? Because I can have more dies on a wafer. So it's like each die, if it works properly, will be a component. So more number of dies, more components, your cost would come down. So there is always a push to reduce your die size. So depending on your die size, you can have so many dies on a particular wafer. Wafers are also available in different sizes. Again, there are different metrics. They are available in different sizes. They are available in different qualities based on what is your end product. Okay, what we get is a wafer. The first test that we do is a wafer sort testing. It's called as wafer sort testing. Basically, whatever the patterns I was mentioning about ATPG, right? We would have generated certain sequences to test my logic. We apply those sequences onto every die in this wafer. Any die which passes would be marked, say, green, and any die which fades would be marked red. Why we need to do this is post this using a laser cutting machine. They cut this and they bring out this each die. Okay, they get each die. It has to go for packaging. I don't want to spend my money on a faulty die. I want to just discard them. I want to package only a good die. So that's where this wafer sort testing comes into picture. So all the good dies go into the package. Again, During packaging also, you can have certain defects introduced because packaging is all like you have to make those connections to the leads and all. So once it comes back from packaging, we run the packaging test, which is again same set of patterns run on the packaged part. Any part which passes, you can call it as a good part which can be shipped to customer. Anything which fails, normally we discard it. Again, when it comes to testing, there are different types of testing. You might have heard about aging test or aging. Typically, how do you simulate that aging? I want to understand how my components will behave, say 10 years from now. What they do is they put it in an oven and they heat it up to a certain temperature for a few days. They bring out that component and again run through some parametric testing. So they will get to know what is the degradation. Based on that, they can say, okay, this chip will work well, or they can give an expiry saying this is for 10 years. Post 10 years, we cannot guarantee you its performance can degrade. So all such testing is done with the support from fab. So typically, if we have TSMC as our fab, so what TSMC does is, post 2 or 3 months after you have taped out the design, they give us the wafer. We have two options. Either we can go with the testing facilities available at TSMC, or we can go outside and look for other cheaper sources. Typically, we choose companies like GUC, which is in Taiwan. Again, TSMC is in Taiwan, GUC is also in Taiwan, or we choose SPIL, which is in Shanghai. They house this ATE. ATE is nothing but a supercomputer along with some robotics. We have to load this pattern to that ATE supercomputer, and it is interfaced with a robotic arm, which basically picks each die, keeps it on the board, applies the pattern. If it is a pass, it puts it to one bin. If it is a fail, it puts it to another bin. Human or interference or interfaces only with that machine. We don't go and pick anything by hand and place it. And as I told you, these are all factories. So they run 24 hours, 7 days a week. And they need to have sufficient design, or as I told you, we have to book our slots. Anyone can book, any fabless semiconductor company, they book their slot for all this testing. So this is just a small introduction into the way testing and the way we decide what is a good chip to ship, or how do you meet those DPPM that is set by the customer. One thing which comes here is yield. Yield is like, say for example, on a wafer, if I can get 100 dies, if all the 100 dies are good, my yield is 100%. Now, I have to test. When I test, definitely I will find some faulty chips. It can't be like 100% yield. Now, the more stringent test you have, more will be the discarded pieces. Right? You also have to take care that you meet a minimum yield so that the company that you work for also makes a profit. So, how do you make sure you meet the yield at the same time you meet the quality? This is exactly the challenge that you also have, we also have. You just don't want to fail everyone, right? That doesn't give a good name to the institution. If you have set a very tough paper, then the number of students who pass could be less. At the same time, we should also look at the quality. The same challenge even we go through. So what we do is we categorize certain tests which are very critical and which we think that any component, if I want to call it as a pass, it has to pass this basic test. Then there are a few other optional patterns. Now, depending on the end product and the application, we will decide whether to try those patterns. Should we make it part of the test program or to leave it? So based on that, we juggle between quality and yield. Okay. So your question is like, if I have 100 dies on a wafer, typically what is the yield? Uh, okay. Um, that depends on your process node. So this is where all those technology nodes that we talk about, right? 65 nanometer, 90 nanometer, 60 nanometer. So this is where it comes in. Currently, all the production designs at TSMC are happening at 3 nanometer. When this technology started as a new technology, the yield were typically in 20 to 30%. But they also learn from the first set of designs that they do, or the first set of fabrications that they do. So as I told you, I was talking about something called as yield analysis. In the first time, say for example, when I said yield is say 20%, so out of 100 dies, 80 dies are rejected dies. We go and try to analyze what has caused this particular fault. And that's where all those analysis of using that electron microscope, going deep into the layers of fabrication, trying to understand where the etching has gone wrong, where the those layers are wrong. So this analysis, there is a tool called as Yield Insight from Mental Graphics or Siemens. So we use that tool and we do an yield analysis. So that's where we get to know, we try to pinpoint the exact node where there is a fault. And when you have 80 pieces to do this analysis, if out of the 80 pieces, say 70 pieces have the fault at the same point, they go back, they tune their fabrication process to reduce this. So the next wafer that they produce can give them or can give you an yield of say 30%. That's a 10% improvement. Again, they do this analysis. So this is how the yield improves. If you go back to an older technology node, a very proven technology node, say 60 nanometer, so yield can be as good as 80 or 90%. So that's where the technology, the newer technology node that you are using, you are at a risk of this yield. So the fab also gives you certain discount if you move to a newer technology node. So typically our test chip and all, we can take that risk because they give certain discounts because they are also in a experimental phase or learning phase. We are also in a learning phase. It benefits both. Not really, but of course the experience of the person does matter, but it's not the major component. Correct. Yes, it's more of a, as I told you, uh, more of a automated process than a manual process. Yes, yes. But the pattern would be given by a person like me. So the person who is sitting there, see, he's like a JCB operator. So his skills also matter. But as I told you, if my patterns are correct, finally, what matters is how have I set the pattern quality at my end when I'm generating the pattern. Definitely, yes. Correct. Correct. But the thing is, as you know, in private industries organization, we have a certain experience level for a person to sit in that chair or to take that responsibility. So a well-proven person would only take that seat. Correct. Yes. Yes. Definitely. See, whatever may be AI and all, but natural intelligence is still required. We cannot. Yes. So these were some of the testing that I was talking about. Packaging test. This is the wafer sort testing. Packaging test. So parametric testing is all the electrical parameters that we have to test. And then there is one point on functional testing. Typically, we don't do functional testing when it comes to manufacturing test. What we do is, as I told you, we would have marked some good chips, right? We will send it to the customer or the client. He runs his or functional patterns on that because functional patterns take a longer time because they have to verify each and every functionality of whatever has been built into that chip. So that typically takes a longer time. So they do the functional testing from their end. And to do this functional testing, you don't need this ATE and all. They can have a board, put that chip, and then start booting the chip and loading their programs. And these were some of the testing criteria that I was talking about. Scan testing, where I was mentioning that each scan element, that's each sequential element, is hooked up into a scan chain. Built-in self-test is one method which I said we apply normally for memory. And there is something called as at-speed testing. You have read about PLL, phased lock loop. Typically, for a chip, there is something called as a functional frequency. A chip would be designed to operate at a particular frequency. Typically, most of the advanced chips, they use functional frequency in some gigahertz, 1.5 or 2 gigahertz. The problem with this clock is, this cannot be supplied externally. Though you have crystal oscillators and various types of oscillators, the problem is you cannot give this functional frequency externally into the chip because there is something called as IO, input and output pads. They have a frequency restriction. They cannot withstand a signal whose frequency is more than 800 megahertz. With this challenge, how do you feed say 1.5 gigahertz? So that's where we insert a on-chip PLL, phased lock loop. And this PLL will typically require a reference clock. Now that reference clock would be in the order of 312 to 512 megahertz. That frequency you can always apply it through crystal oscillator or any external oscillator source. So this PLL, there is something called as PLL locking sequence. You have to lock the PLL. Once you lock the PLL out would be whatever the frequency that you have programmed that PLL to. Now the PLL output would be a continuous train of pulses. We have something called as at-speed testing, wherein we shift at a slower frequency, which we call as a shift frequency, but capture at speed. Now, how do you select between your shift clock and capture clock? So that's where a concept of OCC comes into picture, on-chip clock controller. So these are all IPs. So when you design a chip, all this matters. What's your functional frequency? Okay, if my functional frequency is above 1 gigahertz, then I'm forced to go for an on-chip PLL. If I go for an on-chip PLL, I'm forced to use an on-chip clock controller. So that clock controller is nothing but you can imagine it to be a huge mux which selects between your test clock. Test clock is nothing but my scan clock or the clock which I use for testing for this manufacturing defect. They will be very slow or less frequency clock, typically 10 megahertz to 50 megahertz or sometimes even 100 megahertz or 400 megahertz. But it's definitely less than your functional clock. So it has to shift or it has to select between these two clocks. And this is where all the concepts of setup and hold comes into picture from the testing point of view. Okay, so I hope you know what is setup and hold. One simple question. If you think I have a setup violation, do you think I can work around? You have manufactured a chip and then you find a setup violation. Do you think I can work around? Any yes or no? Why? What is setup violation? Setup violation is the minimum amount of time the data has to be stable before the appearance of clock edge. Clock is in my control. Okay, if I reduce the clock frequency, your pulse or the clock width will increase. So you can delay the clock, right? And give that additional time for the data to settle down. So I can obviously work it around. Any doubts? But the same thing when it comes to hold, you cannot do anything. If you find a hold violation on a chip and if it fails because of hold violation, You have no other option but to throw it away. So that is where the concepts of timing closure, I think I just heard the last 10 minutes of Vijay sir speaking. So this timing closure and all plays a major role. You cannot tape out a chip with hold violation. Even if you tape out a chip with setup violation, we can reduce the frequency and somehow make it work. But with hold, no, it's going to be a discarded piece. For hold, okay, let's go back to the basic definition of hold. The basic definition says it's the minimum amount of time. Yeah, the data has to be stable after the appearance of clock, right? So if I'm increasing or decreasing the frequency, I'm just moving the clock edge, right? So say as per my definition, the hold is going to be after the appearance of the clock edge. So if you move the edge, it is not going to help because this is also going to move along with that, your requirement. Sir.
So the same thing we can.
No.
We can
Why?
say that whatever you do, that is fixed. If you are increasing the devices, for hold also it is the same. Or can we have the both?
No. What I'm saying is, setup you can work around by delaying the clock. Okay, minimum amount of time the data has to be stable before the appearance of clock. If I have a setup violation means clock has arrived but my data is not stable. So what I can do, I can delay the clock, give that additional time for the data to settle down. Agree? But what does hold says? Hold says it's the minimum amount of time the data has to be stable after the appearance of clock edge. If I'm if I'm increasing or decreasing frequency, it's just that I'm moving the clock edge. Right? If you go to the timing domain, it's nothing but the clock pulse width, right? I'm just moving that edge. But your hold definition also moves with that edge. So if the clock edge is appearing here, it will say the minimum amount of time is say 8 ns. That 8 ns, the data has to be stable. So if I move the clock edge again, the same condition will be there. So you cannot work around the hold by increasing or decreasing the frequency. Maybe Vijay sir can give you more details. Right, sir?
Yeah.
You want to add anything? So that's one of the basic requirement when it comes to timing closure. You have to fix the hold. Similarly, you might have seen on a board, on a PCB board, you'll have multiple chips, multiple ICs. So there is a concept called as boundary scan. So wherein we can test all the the IC boundary, right, which are there on that board using a technique called as boundary scan. So where again it's nothing but a huge chain which forms with TDI to TDO and we can test it. So that's where the boundary scan comes into picture. This is more on the board level testing. I spoke a lot about cost and lead, so I'll skip this. So this is the DFT technique which I was talking about, which will help us improve the test coverage. Test coverage means quality and lower cost, because if I can test the chip quickly, it is going to reduce my testing burden. Okay, this is the scan chain which I was talking about. So I was mentioning that your scan chain is nothing but a huge shift register. Can I write on the board? Okay, I'll try to explain. Basically, you know a D flip-flop. D flip-flop has one D input, clock and Q. I'm leaving the set, reset and all just for our sake of understanding. Now, how can I make this a normal regular flop as a scannable flop? What is scannable flop? I'll just write and show you. Not that. Basically what we do is we add a mux in front of the D. So mux has a select line. That select line I call it as the test mode. And then, yeah, maybe I think, no, I was just thinking which one to use, which is, no, and proximity of people. Right? Okay, so this is basically DFF. So this is a simple DFF. I've written D, Q and clock. Now, to make this particular flop a scannable flop, what I do is I add a mux here. So this is a 2:1 mux. So this is my I0, I1 and this is my select line. If my select line is equal to 0, I would be selecting this input A. If my select line is 1, I would be selecting it. Then Q goes to a huge combinational logic and then something comes here. So what I am doing is I am adding a mux here. I0 I'll still keep the same functional. I1 I'll call this as the test input. Now if I want to put my design in test mode, I make the select line is equal to 1. This I will call it as test enable and I will apply my sequence here. So instead of the functional sequence, my test sequence is going into this. So typically if I consider a small scan chain, it would be Q2 SI. I would be calling this SI or TI, right? So when I say TI, internally it's a structure like this. So this particular plot, after all this, if I just rewrite, it will have D, it will have TI, it will have TE, it will have clock, and here this would be Q, also test out. So when my TE or the select line, right, is equal to 1, instead of the functional input, it will select the test input. When my T is equal to 0, it will select the functional input. How this happens is basically using this logic. So the first step that I do in my design is I swap all the regular scan elements into such scannable blocks. So this is the first step which happens during DFT. So this is where the concept of shift comes in, because I was talking about a scan chain which works in the shift mode. Okay, you have any questions or you want me to talk on any of the topics which you want me to bake the chip and then study the parametrics? Okay. 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 Yes, I think there is a software. Sorry, I cannot hear you. IT? Okay.
I just want you to think about how you're going to test the connectors. Connector is the motherboard, and another connector inside the motherboard. So how do you want to connect the signal from the connector from the motherboard to the motherboard? So how do you want to test these two connectors?
Motherboard to the daughter board. Okay. Typically, you might have heard about various communication protocols like SPI, Then there are like SPI square C, right? So they would have used a certain protocol for this communication. So for each of this protocol, it also comes with its own testing. So a particular test vector would be, or there would be a sequence to do this testing, because they would have used the standard protocol. It's not just a physical connection. It would have followed a certain protocol. So using those protocol, we test it.
There are something known as IBIS model and IBIS. So there are model testing for connected
Okay. So I'm not that, maybe I don't know whether I can answer that. Maybe you'll have to give me some time so that I go understand and let you know. Because mine is more at the chip level testing and to some extent at the board level. Okay. Any other questions? Yes. When you say I'm unable to test any one of the block, uh, what could be the possible reason? You are saying this testing during the manufacturing test or during my design? Huh. So if I'm not able to test, if it is part of the scan chain, definitely I'm going to test it. Only if it is a non-scan, then it doesn't come under the scan chain. Is that your question, or help me understand a little better?
My question is, when it comes to scan chain reordering, so you are going to test each and every block.
No, scan chain reordering is something different. You have a scan chain. For certain reason, you are saying I cannot go with this order of the scan chain. I want to reorder.
Because the purpose of using scan chain reordering is to optimize.
Right. So scan chain reordering basically is a requirement which arises from PD. Okay.
So it depends on the DFC logic, right? DFC protocols and all. So you would have inserted some scan chain, the number of scan chains. So in physical design, we release the okay, given this design exchange format is right from the input. Okay, is given by added or by MD to DFC to physical design. So in physical design, during the placement, right, phase of placement, pre-CPS optimization, where we does where we do all the placement of the standard cells, okay, and optimization at the pre-CPS stage. We do whatever is the scan chain reordering for making use of functional. So functional test of the functional class is the main thing for our optimization, because this is operating at lower speed. Suppose that it reorder, there is a scope for reordering of the scan chain. The scan chain will be fixed, but we'll reorder some of the blocks based on the physical location of the register, physical location of the flip flop. That is called scan chain reordering. So, but we are not doing any changes in the modification of the scanning and the scan out ports. Okay, that we are not touching. But for the making use of our trading of the physical design rules and all, for the timing closure aspect and the DRS performance, we are doing the reordering. So we are just reordering. D1 is connected to maybe in the first original scan chain, D1, D2, D2 like that. We can reorder it, but that will not affect anything related to the scan chain. The function at the system. That is to say that after the scan chain, you do this reordering. Yes, yes. Okay.
I'll just add one.
I want to know one more thing. All these scans are done using automation or manually pattern will be checked in your DFT.
Okay.
Why means in the first and all there is a automated code, whereas in the NXP and the ST electronics they are setting the pattern for each of the classes which they are sending this.
Okay, I just want to add one line to the previous question. So when we are doing the scan chain hookup, normally we are not aware about the placement uh, from the physical design perspective. So we would have hooked up in certain default order. So when it goes to the physical design, they look at the routing congestion or timing problem that they can face. Based on that, they rearrange depending on the placement or the floor plan, right? So that's where this scan chain reordering comes into picture. Now to come back to your question, as far as I know, everything is using a tool. Pattern generation is always done using a ATPG tool. To name some of them are like we have Mentor Test Compress, and then in Synopsys, I think there is DFT Tetramax. So it's done using tool. When you say manual, I did not understand. I mean, you cannot do this. You cannot put in something in a file and load it.
They are manually checking each pattern and they are going to pass those patterns.
So when you say manually checking each pattern, how can you check that? I mean, we cannot check by looking at the zeros and ones, right?
So they are checking manually. So I saw that.
Maybe you can do that if your design is very tiny with only a few handful of blocks. Maybe you can do that. But you know, right? The current designs are all huge and definitely manually you cannot do it.
Maybe they are adding some additional patterns just on top of what they are deciding.
Okay.
Make you switch off some logic, switch on something.
No, that sequence anyway you have to, but finally it has to be through a tool only.
In your final chip testing, we are making the full first not chips are there, but in some chips are tested basic critical points that pass. But in for application depends on the medical application. On what basis you will select the other tester, second level tester, testing parameter, and if that passed also, in how we measure those things, whether that particular chip is suitable for only particular medical application, and how do you verify those chips?
Okay. I heard some last 10 minutes of what Vijay sir was talking, and I think he was talking about a few corners, right? So we were talking about some various uh, sign up corners, right? So when he says it's a sign up corner, it would be aimed at a particular temperature, voltage, and other physical parameters. Say for example, if my chip has to work at say Siachen Glacier, I know what's the lowest temperature that it can go there. So when I am designing, when I am testing, I should make sure that I test for these conditions. So typically when you are saying a medical application, so accuracy matters a lot. So my test coverage matters a lot. Again, I should know what are the conditions that this particular end product can be used. So based on that, I have to refine my testing. And as I told you, all that requirements, some of the requirements would be coming from the physical design where they have the sign off corners. It has to work at such a low voltage, or they would say minimum voltage, maximum voltage, temperature, pressure, everything comes into picture.
It means before taking the before designing on this, you will take these parameters from the customer side.
Correct. So this is called as I was talking about a spec or a requirement, right? So if you are coming to me as a customer, so you come up with a certain requirement. Hey Prashant, I need a chip for this. This is going to be the end application. These are the conditions that this particular chip has to work. This is the end product. So I would again ask you further more questions on, hey, what's the maximum temperature? Do you think that this particular equipment may face? Say you are having a dash cam, you are having it inside your car, you have parked your car out in the sun, and you know, right, how hot it can get. And you come, you turn on, that camera has to work, right? The temperature can be double of what the atmosphere or the outside temperature is, right? So all this matters. So we have to consider all this, and based on that, they will do the sign off.
That's why I told you, right, the DFM, DFI timing and all, these are the kind of things. We need to consider all this. We call it as PVT, process voltage temperature.
Right, right.
So these characterizes the model. your end product. Here in glacier or you are operating a high temperature place somewhere you are going, okay, you are keeping that. So based on that, we have the library models available. Based on that, we do the sign off analysis. Sign off analysis we do it on these library models and we do it all the analysis. Manufacturability, yield, and timing, okay, cost, maintenance, so all this. So implementation one part and sign off is again challenging.
Are we done? Okay. So thank you. And I'll just take 2 more minutes to thank our SCSE AC department. And as Sir was mentioning, 19 years back, I was here as a student doing my master's. So I still remember UBM sir teaching a subject related to RF. I forgot the subject name, but I know you used to teach us RF. Similarly, Gayatri madam used to teach us. Veena madam used to teach us, and Natarasu sir was there. I heard he has recently, or I don't know when, 2 years back, retired. Okay. So, and there was one Professor Venugopal. He used to take one subject for us. So it's really happy to be back here after 19 years. So I met a few of my professors for the first time after a long time. So thank you all. So I just want to take 1 more minute and see, I moved to Mysore to start this silicon design in Mysore. One of the easiest thing that you can start in your place is the design, because manufacturing, that's a completely different thing. You need the government push for it. As an individual, as a techie, that the simple thing that we can do is start the design. So uh, I'm very happy to tell you that now Mysore is also a key player when it comes to design. So we are doing a 3 nanometer design here in Mysore. We taped out the chip in December. Silicon is going to be coming in the month of April. So I would be traveling to Taiwan to support this activity. So I'm happy to share, at least we started that first, right? Always taking that first step is difficult. So we have started that. I expect our Proxilera to grow in this direction. So request all your cooperation. Thank you.
Thank you, sir. Thank you so much for your valuable time and explaining about the design and testing of the semiconductor devices. Now I request UPS Smith, SPK Smith, Bas Madam and Veena Madam and the coordinators to facilitate our resource question.
ಇಲ್ಲ ಸರ್ ಪರವಾಗಿಲ್ಲ that's okay. Thank you. Thank you. Thank you, sir. Thank you, madam. Thank you, sir. Sir, ನಾನು ನಿಮ್ಮ ಪರಿಚಯ ಆಗಿಲ್ಲ.
ನಾನು ಡಾಕ್ಟರ್ ಸುದರ್ಶನ್ ಪಾಟೀಲ್ ಕುಲಕರ್ಣಿ ಅಂತ. I'm more into signal processing and control system.
ಮನೆ ಹೋಗ್ತಿರ್ಬೇಕು.
ಇವತ್ತು ನಮ್ಮ ಜೊತೆ
Now we break for lunch. Next session will start at the
ಡೀಟೇಲ್ಸ್ ಅಸೆಂಬಲ್
ಬೇಡ ಸರ್,
ನಮ್ದು ಇದು ಕಷ್ಟ
ಹೌದಾ?
ನನ್ನ